So here is another question on electric potential. It is given that 2-point charges plus 3 microcoulomb and minus 3 microcoulomb are placed 2 into 10 to the power minus 3 meter apart from each other. Calculate the electric field and electric potential at a distance of 0.6 meters from the dipole, the center of the dipole, along the broad side-on position, and electric field and electric potential at the same point after the dipole is rotated through an angle of 90 degree. Okay, so here first let us draw the whole thing. So we have an electric dipole minus 3 microcoulomb and plus 3 microcoulomb. This is, let's say, the center. Okay, minus q plus q. Okay, the separation gap, which is equal to 2 into 10 to the power minus 3 meter. So here it is given, first we have to calculate both the electric field and potential along the broad side-on position. So broad side-on position simply means along the equatorial line. Okay, along the equatorial line. So let's say we have to calculate it at this point P, which is at a gap or distance of 0.6 meters. Okay, 0.6 meters from the center of the dipole. So here another thing, 0.6 meters is greater, much greater than 2 into 10 to the power minus 3 meters. So this constitutes a short dipole. Okay, a short dipole. So broad side-on position, that is along the equatorial line. So all the formulas associated with equatorial line will be applicable. So the potential at point P along the broad side-on position or equatorial line, first we have to calculate the electric field. Electric field along the equatorial line, that is equal to 1 by 4. So we have to calculate the electric potential, electric field first along the equatorial line for a short dipole, that is equal to 1 by 4 pi epsilon 0 P by x cube, where P is the electric dipole moment, which is equal to P is equal to Q into 2a, where 2a is the separation gap, Q is the magnitude of either charge, so that is equal to 3 into 10 to the power minus 6 into 2 into 10 to the power minus 3, that is equal to 6 into 10 to the power minus 9 coulomb meter. So here it is equal to 9 into 10 to the power 9, 1 by 4 pi epsilon 0 that, to 6 into 10 to the power minus 9 by x, the distance of the point from the midpoint of the dipole, that is equal to 0.6 meter, 0.6 cube. So that is coming around 250 Newton per coulomb. Okay, that. And then the electric potential. So it is very easy, along the equatorial line the electric potential, that is equal to 0 volt. Always remember that, no need to calculate anything. Then it is given in bit 2, at the same point we have to determine again the electric field and electric potential when the dipole is rotated through an angle of 90 degree. So here, when the dipole is rotated through an angle of 90 degree, it happens something like this. See, when the dipole is rotated through an angle of 90 degree, the situation is something like this. Okay, this. So now the point P, which was previously along the equatorial line, now it is along the axial line. Previously it was along the equatorial line, now it is along the axial line. So now all the formulas related to axial line for electric field and electric potential, that will be applicable after the dipole is rotated through an angle of 90 degree. So in this case, first we have to calculate the electric field. Okay, the electric field along the axial line, that is equal to 1 by 4 pi epsilon 0 2 p by x cube, which is equal to 2 into 1 by 4 pi epsilon 0 p by x cube. We have already calculated that 1 by 4 pi epsilon 0 p by x cube here. So 250 Newton per Coulomb, so it will be twice of that. 2 into 250, which is equal to 500 Newton per Coulomb. That is the electric field. Then for voltage or electric potential along the axial line, that is equal to, the formula is 1 by 4 pi epsilon 0 p by x square. That is equal to 9 into 10 to the power 9 into p, which is equal to 6 into 10 to the power minus 9 Coulomb meter by 0.6 whole square. Okay, this. So why 0.6? Because the distance of the center of the dipole or the midpoint of the dipole from that point remains unchanged even when it is rotated through 90 degree. So this distance, this gap x remains 0.6. So this is equal to, it is coming 150 volt. Okay, 150 volt. Okay. So here is another question. It is given that if 300 joule of work is done in carrying a charge of 3 coulomb from a place where the electric potential is minus 10 volt to another place where the potential is V volts, calculate the value of V. Okay, so here let's say we have 2 points. Okay, we have, let's say here point A and here point B. We have a charge Q which is equal to 3 coulombs initially located at point A. It is moved to point B. Okay, here. This is the initial point, this is the final point. The initial point potential is how much? Minus 10 volt, that is potential at point A, and the potential at point B is equal to V volts. Okay, we don't know the value of V, we have to determine it. So we know that work done in bringing a charge from an initial point to final point, that is equal to the charge, final point potential minus initial point potential. Here the work done from moving the charge from A to B, that is given 300 joules. The charge is 3 coulomb. The initial point potential VA is equal to minus 10 volt. So for A to B, work done in moving the charge from A to B, it will be equal to Q into VB minus VA. Okay, so 300 is equal to 3 into VB, which is equal to V, minus VA, which is equal to minus 10. That implies 300 is equal to 3 into V plus 10. Okay, that implies V plus 10 is equal to 300 by 3, which is equal to 100. Which is equal to 100. V plus 10 is equal to 100. That implies V is equal to 100 minus 10, which is equal to 90 volt. So the potential at point B, which is V volts, VB is equal to V, which is equal to 90 volts. This here the potential is 90 volts, which was asked. Okay, simple application of this formula. The work done in moving a charge from an initial point to a final point. Okay, this formula always remember.